Hello, welcome to a video that describes factoring quadratic expressions. This will cover sections 4.3 and 4.4 in our textbook. So here we're going to do 8 examples, and they're all quadratic expressions because they all have x squared, and remember a quadratic expression is an expression that involves x squared. And we're going to talk about factoring. Factoring is one of the essential algebraic concepts that you just have to be comfortable with before we move to much more advanced stuff. So it's important that we're talking about this right now, and they'll have a chance to practice it the next time we meet as a class. So let's start with example 1. X squared plus 5x plus 4. So one way you could factor is use trial and error. And the way that would work is you would just figure, okay, well, two things have to multiply to x squared, two things have to multiply to 4, and then when you FOIL it, you hope that you get back to x squared plus 5x plus 4. For example, I could say, okay, let's have x and x, maybe plus 2 and plus 2. But then if I FOIL it, remember FOIL is first, outside, inside, last. FOIL, first, outside, inside, last. I would not get back to the original expression. I would get actually something that's a little bit different. So then you could say, okay, well that didn't work. Let's say you have x and x, plus 1 and plus 4. Oh, I guess it does work because you get x squared plus x plus 4x plus 4. You get x squared plus 5x plus 4. So then you know that to factor x squared plus 5x plus 4, you would just get x plus 1 times x plus 4. I think trial and error, to be honest with you, is a bad technique. And the reason I say it's a bad technique, when we go to example 8, if you think about it, that's going to be a little hard to figure out. Like if I were trying to do trial and error with that, how do I break apart to 12x squared? Do I do like 6x and 2x? And how do I break apart to 6? I do, plus 6 and minus 1. It becomes a little bit too complicated to use trial and error, and there's so many possibilities. It's not a very foolproof method, and not very efficient. So I think trial and error is actually really bad. So I'm actually going to erase all this stuff here. And what you might want to do is cross it off your notes. That's a bad technique. So instead, what I like to do is I like to use the diamond method. Some people like to call it the cross method, or some people call it the X factor because you're factoring and it looks like an X. Any creative name you have, I don't really care. But here's how the method works. You put A times C up top and B down below. Now remember, the general way we write a quadratic expression is ax squared plus bx plus c. So in this case, obviously a is 1, and b is 5, and c is 4. So when I use the diamond method, 1 times 4, which is 4, and of course 5 down below. And what I want to do is find two numbers that multiply to a times c and add up to b. So in this case, what two numbers would multiply to 4 and add up to 5? Well, if I think about it, those two numbers naturally would have to be 1 and 4. Because if you look at what two numbers can multiply to 4, obviously 1 and 4 and 2 and 2. 2 and 2 doesn't work because then you get 2 plus 2, which is 4. We need the sum to be 5. 1 times 4 is 4. 1 plus 4 is 5. So then what you do is you simply just say x plus 1, x plus 4, and you're all done. Let's try this again for number 2 here. So a times c, so a here is 1, because you don't see a number being multiplied x squared, so you assume it's 1. So you 1 times 5 is 5, and b is 2. But then there's a problem. What two numbers multiply to 5 and add up to 2? There are none. That's the reason that there's a reason for that, because of course 1 times 5 multiplies to 5, but they don't add up to 2, and there's no other combination of integers that we could put together that can make that happen. So in this case, we say the answer is prime. If something cannot be factored, we say it's prime. Okay, let's try another one. A times c, it's 9. B is negative 6. Now what two numbers multiply to 9 add up to negative 6? We could do negative 1 and negative 9, but that adds up to negative 10. We could do negative 3 and negative 3. And that works. So negative 3 and negative 3. So you have x minus 3, x minus 3. And that's it. Now this also gives rise to a very special type of factoring, because we can also write our answer like that as well. Either answer would have been correct. In fact, this is called a perfect square trinomial. Tri, because it's 3 terms. Let me spell that better. Trinomial. Sorry, I'll write that better. So tri. And perfect square, because 1 is a perfect square right here. 9 is a perfect square right there. And when we FOIL it, we wind up getting the same thing. So for perfect square trinomials, if you have something kind of like this here, a plus b squared or a minus b squared, we would expect something kind of like this. And we put x's and x's next to a. Actually, hold on. That made no sense. Let me erase that. If I were to FOIL this, I would get a squared plus 2ab plus b squared. That's just multiplying a plus b by itself. And here I get a squared minus 2ab plus b squared. And so you can see how the x squared and the a squareds line up, the 9 and the b squareds line up, and that would imply that a is x and b is 3, which will get me the middle term right there. Likewise with a minus b squared. So whenever that happens, when we have 3 terms and the ends are perfect squares, the first term, last term are perfect squares, and also the middle term is basically twice the square root of x squared 9, and then multiply that out, then you would have yourself a perfect square trinomial. In fact, there's actually a really cool flowchart that I made a long time ago. So if we look at this flowchart, the way it would work is you'd ask yourself how many terms you're given. So obviously in number 3, I was given 3 terms. Are there any common factors among the 3 terms? Well, they had none in common. Are the first and last terms perfect squares? In that case, the answer was yes. X squared and 9 are perfect squares. And then there's a little asterisk. Make sure the middle term is twice the product of the square roots of the first and last terms. Well, the square of the first term was x. The square of the last term was 3. And of course, the product of that is 3x. Double that, that's 6x. So yeah, that did work for us. So that's why I can factor it as a minus b squared, as you see right here. Looking back at some of the other ones, like for number 1, there was 3 terms, but no common factors. The first last terms were not perfect square. Well, actually they were, but the middle term was not twice the product of the square roots of the first and last terms. So in that case, I just factor using a diamond. But we're going to see some situations where the leading coefficient may not be 1, or we're factoring quadratic expressions of 2 terms. So let's move on. Let's go to number 4. So in this case, we have 2 terms. So let's actually look at the flow chart now that we have it here. Are there any common factors? Nope. Does the expression represent a difference of 2 squares? It actually does. Because if you think about it, if you have something like this here, right, and foiled it, you get a squared minus b squared. So in this case, I have x minus 5 and x plus 5. And that's it. We're done. Or, if you want to do what we did earlier, a times c is negative 25, but there is no b, so it's 0. So it has to split as 5 and negative 5. So you could do number 4 like we did number 1 and number 3. But if you just think about it, that's a difference of 2 squares. Because you're subtracting 2 terms and they're both perfect squares. Now, if you didn't have that, then you're done. So that would be the case for number 5. So yes, we have 2 terms, no common factors, but it's not a difference of 2 squares, it's a sum of 2 squares. There's no such factoring for a sum of 2 squares. Just can't be done. Or no such factoring rule. Unless you pull out some common factors, that's fine. Like if you had 2x squared plus 50, I could factor out a 2. But in this case, we're done, so we'll say it's prime, because that can't be factored. Okay, let's take a look at number 6. So number 6 is a little different than all the other examples we did, because a here is not 1. So the leading coefficient is a number other than 1. So how many terms, 3 terms, are the common factors? Well, let's check. Do these 3 terms here, 2x squared, negative 6x, and 4, have something in common? And actually they do. There is a common factor. That common factor is 2. So you got to pull it out first. Then what I'll do, are the first and last terms perfect squares? Nope. Is leading coefficient 1? Not anymore now, because now we just have x squared. So factor just using the diamond. So 2 and negative 3, I could break that apart as negative 1 and negative 2. So you still got the 2 from before, don't forget about that. But now you got x minus 1 and you got x minus 2. So now that is factored. What about in case of number 7? Well, in this case, we have 3 terms, but none of the terms are common. Like, 3x squared, negative 11x, and negative 4, I don't have anything in common. And 3x squared and negative 4 are not perfect squares. And the leading coefficient is not 1, so I'm going to have to factor a little differently. So I'm down here, factoring using the diamond. But then I also say, then grouping. We'll get to that in a little while. But let's first do negative 11. Oops, sorry. That should be negative 12. And the 11 should be down below. So what 2 numbers multiply to negative 12 and add to negative 11. Well, if you think long and hard about it, it should be negative 12 and 1. I mean, you could do negative 4 and 3, you could do negative 6 and 2, but negative 12 and 1 would actually work good for us here. So then we go to factor, but you can't say this like we did earlier with some of these other problems with like x squared minus 6x plus 9 or x squared plus 5x plus 4. After I did the diamond, we go straight to the factor form. We don't have that luxury with number 7 because if you FOIL this, you get x squared as your first term, not 3x squared. So that can't be done. But really what's happening here, without really realizing it, but now you will because I'm telling you, you're splitting the middle term. And that right there is a middle term. So really in essence, what we've done is we can rewrite this as 3x squared minus 12x plus x minus 4. So this expression that we had earlier is no different than saying 3x squared minus 12x plus x minus 4. Now, we do something called factor by grouping. Factor by grouping is something you can do when you have 4 terms. And it's really easy. All you do is group the first 2 terms, group the last 2 terms, leave the plus in the middle, and then pull out common factors from each group. So the first group, the common factor is 3x, so I get x minus 4. Nothing's in common between x and negative 4, so I'll leave a 1 on the outside. And notice how 3x is being multiplied to x minus 4. 1 is also being multiplied to x minus 4. So it's almost like you could factor out x minus 4 as an entire group, leaving with just the 3x and the plus 1. So if you pull out the x minus 4, leave behind the 3x plus 1, and now you have it factored. So this gives us a more foolproof way of factoring the more complicated trinomial expressions or quadratic expressions. Okay, let's try one more here. So again, I'm going to do the diamond, negative 72 and negative 1. And we want to think of 2 numbers that multiply negative 72 and add to negative 1. A little bit of trial and error, but if you're ever confused, you can always use your calculator and just start computing a whole bunch of factors to see what 2 numbers multiply to negative 72 and add to negative 1. Well, in this case, it will be negative 9 and 8. So now, I can split the middle term. We'll do 12x squared plus 8x minus 9x minus 6. And notice how I deliberately put 8x first and negative 9x second. It doesn't really matter which one you put first. Like here I did negative 12x first and x second. But if you do it the way I just did it right now for number 8, when you factor by grouping, you got to be careful and make that plus negative 9x instead of minus 9x. Because if you didn't do that, let me backtrack a little bit. If you didn't do that and just put parentheses, now you're saying you got negative 9x plus 6. So negative 6 now became positive when it shouldn't have. So you got to do this. Pull out common factors. So if we got 4x, 3x plus 2. We pull out a negative 3, and of course it's 3x plus 2. Pull out the 3x plus 2, that's a common group there. 4x minus 3. So now we got a really nice way of factoring this. So that basically completes this video. Going back to the flowchart, which will be available for download on our agenda, we haven't quite done factoring 4 terms, but of course we kind of did that for number 7 and 8. It's not that bad. Again, group the first 2 and last 2 terms, make sure there's a plus sign between both groups, factor the common terms from each group, and then combine the outside terms to form one group, leave it multiplied to the other group. So we kind of done all this stuff here. There's also another technique I could show you for factoring quadratics, like number 7 and number 8. It's actually what I like to call the magic box. I'll show you that in class. It's going to be a little bit too overwhelming to show it to you in this video. So we're all set, and I'll see you guys next time. Goodbye.